So I'm coming from Paris and I'm going to talk to you about cold, no, I don't want that, just a pointer. Cold atoms for Casimir-Polder measurement. And so there are not so many cold atom experiments working on Casimir. There are a few, I will present a few to you. And the experiment is a large and complicated experiment, but the whole goal is to measure Casimir-Polder. So don't worry about the experiment. First, just to remember by the past and now who is working with atoms. Now, we have seen many experiments working with bulk and squid and things, but with atoms there are not so many. And in fact, as I'm French, I have to start every speech by citing Serge Haroche. So he's the one who started working with Rydberg atom, going through two plates, and then he were able to measure some effect due to van der Waals or Casimir, etc. at this point. And it was the first who was working on the beam. And after that, nanotechnology appears in the beginning of 2000, and people in MIT were able to make nanograting, transmission nanogratings, 100 nanometer pitch by UV techniques. And then Pritchard and some people in Germany just had the idea to send a supersonic beam inside this nanograting and watch the diffraction picture and measure things which are going through. And they were able to measure some Casimir-Polder effect. Very nice experiment, very complicated as well. But the thing is, supersonic beam means that atoms are going very fast, 2000 meters per second, more or less. And the effect is quite small because they're going through the membrane, through the nanograting, quite in very sudden time. And the effect was small, but they were able to measure something with claiming an accuracy of 10%, and but in fact it was maybe 50% of accuracy on the coefficient and the measurement. But it was the first measurement on that. And in fact, in the same time, the cold atoms appear. Here there are experiments with cold atoms. And once you have a BEC and a plate, if you send blue light on the plate and with an evanescent wave, the BEC can be released and it can bump on this blue repulsive potential. And the attractive force plus the repulsive force is a way to measure the Casimir-Polder. So that was kind of first experiment with BECs for measuring Casimir-Polder. And still, there are people in Germany who are working on that, and they were able now to measure the intermediate range of Casimir-Polder. So this kind of experiments are continuing. But the thing is that if you have a BEC, the wavelength on the side of the BEC is large, and so the distance between the atoms from the BEC and the surface have to be large enough, few hundred of nanometer. But it's still a good experiment. In early 2000 as well, Shimizu in Japan just make holographic, so it just release atoms, they just fall down from a MOT or BEC, and on the surface they just spread off, and they make an hologram here. And the way of making a nice hologram is to take into account carefully what happened on the surface and attractive, repulsive, and things. So it was one of the first people making that. Another way, Cornell make a BEC very nearby a surface, and he was able to measure very sensitive things like a very small DC field from atoms which just stick on the surface. But as well, it's not a good way to measure Casimir-Polder because the BEC is large and the distance is different, and it's large as well. So it's very sensitive measurement, but not very close to the surface. So if you want to be closer, it's not the best way. In Villetaneuse, there is Daniel Bloch, Marcel Duclois, and now Athanasios Laliotis. And they are working in a vapor cell. So it's this time is not cold atom, but very hot atoms in a cell, and the distance between the two windows of the cell can be less than 1 micrometer. And if you send laser and do spectroscopy on this vapor, you can have nice and interesting measurement of the Casimir-Polder and temperature effect. And that's what they are doing now, and now they want to put a Rydberg inside as well. So that's another way to measure some things. And in fact, taking back the gratings, Marcus Arendt in Vienna just sent molecule through nanograting and measure the diffraction pattern, and as well was able to think about, is that a good way to measure Casimir-Polder? What happens if the molecule is going through 1 slit, 2 slits, etc. And in fact, we can see here as well, the distance, the amplitude of the peaks here is not perfectly symmetric. We'll come back on that. And with Stefan Shields, they say, okay, it's too complicated if you want to make an accurate measurement. We did the experiment, it's good, but it's very hard to make an accurate measurement. And the thing is that now we are going to do such a thing with slow atoms. So the talk will be the experiment. It will be 2-3 slides. But in fact, these 3 slides are 90% of my time. And the rest of the talk is only 10% of my time, but that's exactly what we want to do. So we'll speak about the model and what we are doing. So experiment is as that. It's a large experiment. Here we have a huge machine, so 3 meters long, in order to create a supersonic beam of argon metastable. So argon is a noble gas, and then in order to make it metastable, we have an electron gun going through the beam. Electron goes very high in energy, and the sum of this atom get down to this metastable state here, and stay 30 seconds on this state. So which is largely enough for us to do everything we want then. And what is interesting about this state is that it's a cycling state at 811 nanometer, in order to manipulate atom with laser. So it behaves like alkali, but it's not alkali, and once this metastable state argon hits the surface, it comes back to the ground and doesn't destroy the surface and doesn't stick on the surface. And another important thing is, once the atoms reach the detector, it's doing a click, and so we can measure accurately when the atom is hitting the detector on the black background. So that's a nice way to measure the atoms, and this way of making was very useful for making correlation as well. So come back to the experiment. We are making here the fast supersonic argon metastable. We trap them in a magneto-optical trap. So here they are trapped, they are stuck there. And then we do a sequence technique in order to push them with a laser here, to accelerate them at a given velocity. The velocity can be choose between 15 and 40 meters per second. And then we adjust the velocity, we choose one, and we keep this velocity. It's a pulse technique, so the atoms are going from this point, go straight to the detector, pulsed in a pulsed sequence. So with the time of flight, we're able to select a distribution of atoms which is less than 1%, with an absolute measurement of the velocity which is as well less than 1%. And this is the strength of this experiment. Then we have a known, perfectly de Broglie wavelength going through the thing we want to study. And the thing we want to study just is put it in the middle of the beam. And for example, and for what we are speaking here, just we will put a nano grating. So the nano grating is made by ourselves. So we spent some time to learn how to make it. So Nathalie Fabre made it in clean room in France, whatever. And the thing is, at the beginning, we just took some nano grating that have been made in MIT in 2000. But the thing was, the uncertainty on the distance and the measurement and the size and the geometry of this grating was not well known. And we had a lot of trouble to interpret the signal we had. So we decided to make our own in order to be able to cut it, measure it carefully, and redo the sequence many times in order to have the best accuracy you can have on the geometry of this nano grating. So just be careful here, all this part here will be removed. Of course, it's a transmission nano grating, but this is a way to measure as careful as much as we can the size and the shape of this grating. And here is a picture when you can see the transmission, and it's totally transparent in the slits. So the size of the one I will speak about is 200 nanometer pitch, 100 nanometer slits, and 100 nanometer width. I will come back on this number because they are wrong, of course, but that's the whole range. And now we are able to divide this number by a factor 2, so we can make smaller if it is interesting. Doesn't matter what we want to do. But first of all, we have this, and the matter is Se3N4, which is a nitrate silicium or silice. This is a usual system in a clean room. So from that, it's easy to cut, to change, to increase, to decrease, etc. The thing is that this matter, we can have the epsilon as well. We'll see that later to understand what to calculate accurately the Casimir-Polder. So once we have the slow atoms, the nanograting on the detector, what we detect is a diffraction spectrum. So typically a diffraction spectrum for atoms which are going at 19 meters per second. And as you can see here in milliradians, the size of this diffraction is quite large compared to the one which have been measured by the past. It's proportional to the velocity. So if the velocity is 20 meters per second compared to 2000, of course, you have an increase by a factor 100. So that's natural due to wavelength. But there is something else, and here in red, it's a theoretical curve. It doesn't look like, but it's a theoretical curve. Just assuming the wavelength, or atoms at this velocity, without any van der Waals, or Casimir-Polder. So if there is just a grating, they are going through what happened, or what should happen, it's something like that. Which we have something like 2 or 2.5 times larger width in the diffraction picture, which means that all this signal is coming from Casimir-Polder. And what is the message of what I want to tell you is that in such a situation, most of the signal is coming from Casimir-Polder. So if we work enough well, we should be able to have more information than other experiments because we have naturally more signal from Casimir-Polder. So that's a good point, and now we have to work well to deal with that. Okay, so the thing is, now that we have this diffraction picture, how we make the model to model it and what we have to take into account. So first, the source. Source is coming from a MOT, so a magneto-optical trap. It's not a point-like source, so it has a certain size. So we have to deal with that. And we need to put a slit in the front of the grating. Here is the grating. The picture is not that good. Here is the grating. Here is the detector. And here is a slit in the front of on the grating. So the thing is, what will be the angular aperture, the angle from the effective source which arrive on the grating. This is an important point in order to understand and to model what will happen. And another way to say that is coming from optics, Van Sitter-Zernike theorem. You have a source, incoherent source. You go through a small slit, and after, if the slit is sufficiently small, you can have coherent effect. By coherent, I mean one atom coherent. It's not two atoms because it's not a condensate, of course. So this is nice and quite simple way to understand it. In fact, I will use it for the next slides, and we'll see at the end that it's not enough. But for the first approach and relatively high velocity, it works well. And from that, we can explain easily that atoms can go through several slits. So they do interfere one by one, of course, and makes the diffraction peaks, this one. This one are made from this atom going through different peaks. Yes?
What is the size of that first slit?
The size of the?
The slit. The first slit. The one you showed us. The previous slide.
The size of?
Yeah, the slit there, before the diffraction grating. The size of the slit before the diffraction grating.
Yeah. 300 micrometers.
Oh.
The total size of the nanograting that we were able to make is 1 millimeter square, and it's too large. And it's too large in the sense that it destroyed the coherence here. And it's nice to have this coherence peak, so we decided to make it smaller. That's the only thing. Oops, where is that? No, here. So we have the Van Zernike theorem who will help us to understand these diffraction peaks. So according to the fact that we were at this time at sufficiently high speed, we can use the Huygens-Kirchhoff principle in Fraunhofer regime. And so the intensity at a given angle is simply the square, of course, over all the slits, over all the widths inside the slits, of the total dephasing inside the slits, and here the coherence coming from the Van Zernike theorem. So inside we have just optical paths, which explained simply what happened at the broad range in terms of just diffraction through a grating, and we have to add here the phase coming from Casimir-Polder. Otherwise, we can't explain anything. So coming back to this phase from Casimir-Polder, we just use a simple approach for the beginning. So we have the optical path in econal approximation. If we do the math, at the end, we have to integrate over all the distance inside the grating what happened through the potential. So the thing is, this is working well if we have the potential which is smaller than the kinetic energy. That's a very important assumption by Kirchhoff, who said all of that of the optical that we use every day is working if the difference in the potential is smaller than the kinetic energy. For optics, another way to say that is if the difference in the index is smaller, is larger than the difference in the ray light inside the medium you are crossing. So that's worked well according to this. In fact, we'll see that it's not even working anymore at some point. But in the first approach, that's what people done a long time ago. So the Casimir-Polder that we are working with is simply atom matter. So atom matter in a first approach will be minus C3 over Z cubed. Z is the distance between the atom and the surface. And this is van der Waals. That's the first approach. We are very nearby the surface. We can say, okay, that's van der Waals. So we use this, and we'll see what happens. You know better than me that C3 can be calculated this way with the dynamic polarizability of the atom and the surface permittivity coming from the matter that we are working with. So let's start with that and see what happens. For the atom, so that's argon metastable. We take 15 transitions of the atoms. And in fact, we estimate that the core effect from the atom is negligible here. It's less than 1% on the total transition. But if we go to larger atoms, for example, krypton, xenon, that can be a problem, and we have to deal with that. But in this situation for argon, or neon, or helium, it doesn't make importance. So we just take the peripheric electron situation. We doesn't take into account the core effect. So that's for the atom, and for the surface, we found the optical response. And in fact, it's not that simple not to have it. Okay, there are some people who made it times ago. But the thing is, the argon has some transition in UV, and we need to have a nice accurate measurement in the UV regime to make the better calculation for the Casimir-Polder van der Waals interaction. And it's not that tricky. So once we've done all of that with the measurements that we had to deal with, we estimate, but it's not rigorous, that the C3, so the coefficient that we calculate, have an error bar of 10%. Because it's hard to know the matter exactly how it is, and that's the main problem of this. Is that the main problem? I don't know. We'll see later that 10% is enough to discriminate something in a model, but that's something which is realistically problematic for what we want to do with the matter. Okay. So now we have to make the fit. We have all the ingredients to make the fit. We have the C3 coefficient. We say that we are in the van der Waals approximation. We have the source, and we just have to put everything in a model. So the velocity is known with absolute value. We know the distribution. The coherent source is known because we know the size of the mode, we know the size of the slit, etc. We know the period of the grating, the slit width, the grating depth, and we can put all of that in the model and see what happens. And then we estimated the C3 by the calculation I showed you before in a range of 1.25 atomic units. Maybe you know better in milli-electron-volt nanometers cube, so it's 5 millieV nanometers cube. Okay, so now something happened, which is the visual and interesting. Here is the grating, the nanobar in blue. Here is the atomic beam, which is coming. In fact, we have atoms everywhere, and atoms which are hitting the surface, the front surface of the nanograting, because they are metastable, they lose their metastability and they lost for the signal, so we don't care about them. Atoms which are inside, what happened? Here I plotted a calculated classical trajectory in the potential with the C3 I calculated. I exaggerated the coefficient just in order to have a better look of what happened. It's a little bit less, not that less, but it's a little bit, the effect is a little bit less. So atoms which are too close to the surface have been attracted, and those ones just disappear to the signal as well. The only one which we are able to detect are the ones which are going through. And if we measure, or if we calculate here how many atoms regards to the one which are coming at the beginning, there are not that huge amount. This cutting position here in terms of nanometer for 26 meters per second, it's 13 nanometer. So the distance here for a depth of 100 nanometer is 13 nanometer. So it's not negligible at all. And that's a very good point in a sense that if there is rugosity here, we are not sensitive to, because all the atoms which are very near by the surface just have been attracted. So that's another good point, which we are not expected at the beginning, but that's something interesting. That's the first thing, and the second thing is this distance here is something that we put inside the model as a phase, a maximal phase, and all the atoms which are here will be suppressed in the model. Sorry, my mask is terrible to speak. Okay, that's it. So now we have everything, and we can make a fit, or we can just put all the data in the model and see what happens. So I don't know if you see it well. In fact, it's so good that we can see black is experiment and red is theory. So first sight, it looks quite perfect. So yes, you can see there is some discrepancy here as well, some few things. But we can say, okay, that starts to be interesting. You start to have a good model, and so maybe we can start to discuss. So let's discuss. Now I'm going deeply in the calculation process and the fitting process. Over there, all the parameters are good, and now I'm going to make a Chi2 calculation, and this Chi2 calculation is basic one here. Later on, I will tell you something more serious, but here's the basic one. Just take data minus theory over data, in fact, which is wrong. I should have been theory here, but whatever. Afterward, it's better. So we just do a Chi2, and we calculate the Chi2 for all the parameters, and then we run all the parameters. You see, we have a lot. So what I will show you is a map in 2D. If you have one parameter, you're looking for the minimum of Chi2, so it's easy to understand. If we switch to two parameters, the minimum of Chi2 is inside, is on the surface, and we are looking for minimum in this 2D parameter. That's the usual thing. Here we have 7 parameters, so it's kind of tricky, but anyway. Here I show you something which how to say, we imagine it, but now we have a proof. Here is a C3 coefficient. Here is a width on the grating. And I calculated, I don't know, 1,000 theoretical curves everywhere, and then do the Chi2 and with the experiment, okay? And so in white, the Chi2 is huge, so we don't care about it. And the red and blue are the minimum of the Chi2. So this curve is showing you that in all this region where it's blue, you can find a fit as good as the one I showed to you before. So it means that we have a linked parameter in a model that can give you the same fit for a given experimental result. So here we start to feel uncomfortable, of course, because if we have a bad measurement on the slit, we have a totally wrong C3 coefficient, so we measure Casimir-Polder with a huge uncertainty. So this is very important to know and to deal with. Another cross-linked parameter is the depth, the depth of the grating and the distance of the size of the slit. If it's long, if the grating is longer, you can have a larger slit, and if the slit is smaller, you can have a smaller depth. So it's as well a crossed parameter. So that's another thing which looks complicated. And in fact, here from this curve, I can show to you that if we have an uncertainty of 1 nanometer on the width, that gives you 5% uncertainty on the Casimir-Polder coefficient. If we have 5 nanometer uncertainty on the depth, it gives you 6% uncertainty on the coefficient, which is huge, okay? So I have to speed up, I think. So the thing is, let's measure this nanograting as careful as we can. So if we do that, we found this value. Of course, this is totally stupid, because that's the best we can do with average, but we know that from the clean room, they can't tell you more than 5 nanometer accuracy. But by doing average picture, we say, okay, maybe it's in this area. And the depth is smaller, and it's not 100 nanometer, but maybe more, 99, etc., etc. So doing this carefully, we come back to the calculation, and we say, okay, with a massive table. I told you that we did the calculation with van der Waals, but of course, maybe it's not van der Waals, but Casimir-Polder with retardation effect. And so in order to make simple calculation, because you know better than me that this is huge calculation, we used a Williams type calculation, which is a very simple approach to mimic what happens if we are in the retarded regime. And in retarded regime, it means that the C3 coefficient is a function of Z. And doing that, it's a nice approximation of retardation regime, which means that in our case, in our case, here, 15 nanometer up to 50 nanometer. So here is the nanograting. The C3 coefficient is decreased by an order of 15%. So it's not zero, it's not big. Are we able to see it or not? That's the main question of our paper. And the answer is yes, we were able to see it. So here is the C3 coefficient in the Chi2 minimum calculation. Here is another parameter which is not very interesting for discussion here. It was very interesting for the paper. But that makes a nice picture with the round stuff. In blue is van der Waals. In red is retarded regime. And here is the expected value. But you have to know that this is with a range of 10% accuracy around. But 10% regards to the 15% means that we're able to discriminate between both models. So it means that at such an accuracy, we were able to measure Casimir-Polder with the retardation effect. So it was a great moment because it's not that obvious. So here, just to show the difference in the curve, it's very small, as you can see, between the retardation and not the retardation, but we were able to discriminate. Okay, this is now, if we decrease the velocity, all of that was at 26 meters per second. If we go to 19 meters per second, in fact, now the model that was presented to you was wrong. And here is the demonstration. In red is the Huygens-Kirchhoff model. And you can see low in the wings, far in the wings, doesn't fit. And in blue, we spent almost 2 years to make a time-dependent Schrödinger equation in 1D with a collaboration with Nasser Galoul and Ernst Rasel. And now we're able to do it. And of course, it's better. And here you can see just by eyes it's better. And it's better mainly because the potential at low velocity in this area, maybe I can come back, in this region, potential here in this region is not negligible regards to the kinetic energy. So that's here where the Schrödinger equation is much stronger than the Kirchhoff model. So of course we have better accuracy, this way. And from that we can start to improve the model and try to have a better, lower velocity and better model, so we can imagine to have better measurement. And in a sense that we want to do measurement, accurate measurement, we have to discuss with people who are doing metrology. In our lab, we have Benoît Darquier, who works in the metrological groups, and also he teaches us how to do metrology. And the first thing he was saying to us is, okay, Chi2 is not the good one because you have very low signal in the wings, so you have to take not the Chi2 usual, but it's multinomial statistics. So it's not the same Chi2, so now it's more rigorous. We have the good Chi2, we know how make the goodness of fit, and from that we can have the statistical error on the C3. And I finish with that. So today, the statistical error on the fit for low velocity spectrum is less than 1%, which is great, it's amazing. But be careful, the systematic error, which is linked to the goodness of fit, is not approved yet, because the model doesn't fit in the goodness of fit. We are still too far, and there are few reasons for that. One of the reasons is this one. Here is a curve with not a lot of statistics, But as you can see, the first order here is larger than the -1 order. What happened? In fact, we have seen, and we are not the only one who have seen that, if the grating is, no, this way, up. If the grating is not perpendicular to the atomic beam, there is a discrepancy on the distance between the order. It's very sensitive, less than 1 degree, at least 0.2 degree. So if we are not exactly at the good position, there is this stuff. And of course, if you want to make a fit with that, and your model doesn't take into account this phenomena, you cannot have a good model. So that's the main problem we have now. Make a 1D Schrödinger equation with an angle is not that tricky at all. We are working on it, but it's not. And the thing is, from that, once we are able to have a good model with that, we can do tomography, and that's very exciting. We have one grating. We don't know the size of this thing with accuracy better than 5 nanometer. If we tilt it by few angles, we have different diffraction picture, a good model who are able to take into account this angle with the Schrödinger equation. So different information, a known angle with the piezo, which is better than micro-radians. Of course, we'll have more information. And the hope is to decorrelate the geometry and the potential. And if we are able to do that, then we'll have access to the 1% accuracy on the potential because we know the geometry as well. So that's it. Maybe some future. If we have 1% accuracy, of course, we can squeeze or at least participate to the run for the fifth force excluded region. In dot here, that was a measurement done by Jacques Viguier in Toulouse in such a nanograting, but at with a supersonic beam. Now with our accuracy, we can decrease by few order of magnitude here, so it can be competitive or at least participate to this data. Another thing, if we are able now to control and measure, but mainly control Casimir-Polder, we can imagine to have an interferometer. And the thing is, if we have a smaller grating, well-known velocity, and everything is controlled, we can have a looped interferometer. And that's very interesting because actually, the interferometer in this configuration, the Seignac interferometer, are made with light, and fluctuation of intensity is light, make troubles and things. And here we will have Casimir who is doing the job for us. So that could be very interesting. And I think I'm finished with that. So we are in Wiltaneuse with people here, collaboration with Hanover, Rostock with Stefan Schill, and my group there. Thank you for your attention.
Okay, thank you very much. We have a question over there.
Hi. So I have some questions. The first one is, in this kind of experiment, it's very delicate to control the cleanness or how clean is the surface. If you have atoms which are adsorbed to the surface, they create dipoles, and this destroys everything. This is well known. So first question is, how you take into account this? Because you have a lot of atoms which pass through and will be deposited, will contaminate everything, so it will be a mess. The second point, you always speak about this C3. But why C3 is a pertinent parameter in your physics? So can you, this is just an asymptotic value and asymptotic behavior in general. So in your case, can you show us that C3 is the pertinent parameter by plotting because you can do the exact calculation of the force at all distances. And typically the behavior is not necessarily Z3. So why you do not use simply the exact one? And the other point is that you have corners, you have not a simple flat infinite surface. So at the corner, C3 is even less pertinent because you have effect of corner. Do you take into account also this in your theory? Thank you. So,
first question, we are using metastable argon, which is noble gas, and we know that if it's touching the surface, then it goes to, it's not enough strong. When the noble gases touch the surface, it doesn't react with the surface. So there is no problem with that. But you're right about the density. The flux on the nanograting is very low due to experimental problems or apparatus, that's not a problem. So we typically have 10 atoms going through the grating by each pulse. So the density of atoms which are hitting the surface, which can make an extra electrical troubles, are very, very low. We try to estimate it's negligible. And there is no deposition on the surface because it's noble gas. So that's a good point. It's more complicated to make, the argon metastable, but we don't have the problem that is usual with alkali. Alkali will be a terrific problem with that. But from what we have, it's okay. Then the C3, in fact, this way of speaking is this C3. It's just because for us it was much faster to calculate than the full calculation, because we need to have 1,000 calculation to make the Chi2 stuff, and that's the only reason. And the second one is this approach here is not that far from the exact calculation in the region where we are. In first approach, here, you're totally right. I can do it here. Where is that? Yeah, here. I assume that there is only the interaction from one surface plus the second one. I'm not telling that there is interaction between both surfaces, which is an additional parameter, not parameter, which is in fact here as well. The effect estimated by Stefan Schill, we made the calculation and we compare the two calculations, is less than 1%. So we say, okay, we take the first order for first because our experiment is already it's already in a range of 10% accuracy. So if we have better accuracy, then my hope, and I want to, go to the exact model. But we are not here yet. Once we have enough accuracy, we'll go to that, of course. And that answers almost your last question about what happened here and here. Because here is the corner. And of course, it's not see-through about Z cube. That's totally true. But I estimated that here, the dephasing here and here is in a range of few percent for the total dephasing going through the grating. So yet we are not able to put it in the model, but that's the next step. Once we know that everything is correct, we have a goodness of fit, then we'll have to put the correct potential. And I hope to do that soon.
Okay, we have one question more, I guess.
Thank you, Gabriel, for the nice talk. I am not very familiar with the physics of argon metastable, but certainly the fact that you're working with the noble gas is very good for the problem with absorption. So which is the characteristic spectroscopic behavior of argon metastable? Where are the strongest lines and at which frequency, at which wavelength we will see them?
The main line is 811 nanometer in near infrared, and so it's a cycling transition. And one thing we'd like to do as well, but not easy, but just to make the atom in a superposition of state just before going inside the grating. That's something we'd like to do, and it's possible as well. From theory, it's possible, but in terms of time for propagating and decay, it's rough, but that's something we like to play with.
So you're saying 800 nanometers, so it's also the same order of the wavelength that you have with alkaline atoms, right?
And that's why we have the retardation effect, which
Correct.
is not negligible. Absolutely.
Correct, because the characteristic distance at which you will
exactly.
see it's 150, I will say, because it's the reduced wavelength, and then you are by 50.
Exactly.
All right.
If it would have been 2 micron, it would be negligible. Absolutely.
A quick question. So how do you discriminate between electrostatic forces between the argon and the grating and the Casimir-Polder? Is it easy to say it's negligible, the electrostatic forces?
Which forces?
Just plain electrostatic forces from the surface of the grating and the argon atom.
The electrostatic forces?
Because of the potential differences, on the surface, there'll be charges on the grating.
Yeah, the nanograting is grounded, and if there is a small electric field, in fact, the argon doesn't feel it so much. But we'd like to make an electric field, activate with the two plane, and make a non-electric field to compensate or make an extra effect with such a stuff. So that's something we like to do. Actually, maybe there is one, but we estimate that it's negligible, and the model yet doesn't tell us that it might be a problem. But it's very hard to know if there is a residual electric field somewhere, which could make some difference in the potential. My guess is there is nothing, but nothing regards to what? That's always a question.
Okay, thank you very much. I think there are still some questions. I don't know if you want to continue or want to go to the coffee break and continue there. Okay. Yeah. So thanks, Gabriel, again, please.
Thank you.
And we continue